Well, hello, and welcome back to another episode of Quantitative Bites. It's great to see you all. I hope you're doing well. So in this video today, I wanted to talk about another aspect of linear algebra. So continuing from where we left off, in the previous video, we looked at implementing a basic class in C++ to allow us to work with matrices, and we talked about how matrices are one of the fundamental elements of linear algebra and how linear algebra can be incredibly useful in scientific computing and engineering domains. What I want to talk about specifically today is the problem of inverting a matrix. I'm going to start by really introducing the concepts behind this in terms of why we might want to invert a matrix in the first place and what, of course, it actually means to calculate the inverse of a matrix. So there are different ways that we can approach the problem of inverting a matrix. There's a method of calculating adjoints and the determinant and then using those to calculate the inverse that way. Or we can do it using Gauss-Jordan elimination, a process called Gauss-Jordan elimination. And it's the latter of these, Gauss-Jordan elimination, that I've chosen to go with for the code that I've decided to implement. No particular reason, it's actually rather a nice algorithm. It's a particularly interesting way of working, and it presents a particularly interesting coding challenge. To take the basic concepts of Gauss-Jordan elimination and to turn those into code is actually a very interesting problem, as we shall see. Now, as with the previous video, I've decided to split this video up. So this first video today is really just going to go over the theory of Gauss-Jordan elimination and of using that process to calculate the inverse of a matrix. And I think that provides enough material really for one video. I think if I was to then combine that with how we can go about writing code to implement this method, it would rapidly become really far too much for just one video. So I've decided to keep it a little bit short today, and we're going to stick to just looking at the theory. And then in the next video next week, we're going to start looking at how we can write code to actually implement this algorithm. Okay, so without further ado, I just want to say, as I always do, that if you like this video, please do remember to hit that like button, and if you haven't done so already, please remember to subscribe to my channel so that you don't have to miss any future videos. I do try to post a video once a week, so if you subscribe, you don't need to worry about missing anything. Thank you very much. Okay, let's jump over to the computer and let's see what we can learn about Gauss-Jordan elimination and calculating the inverse of a matrix. Okay, so I want to continue with our discussion of linear algebra algorithms in C++. We are really, before we begin talking about matrix inversion and Gauss-Jordan elimination, I want to just provide a little bit of an introduction to precisely why we might want to invert a matrix in the first place. Well, the simplest way of illustrating an example of why we might want to do this would be to look at solving systems of linear equations. So if we consider a system of equations like this, so we have three equations here and three unknowns. The unknowns are x1, x2, and x3. The coefficients of the three equations are represented by a11 through to a33, and then the answers, or the results of the equations, there by b1, b2, and b3. Now, of course, we can represent that in matrix notation in this way. So we take all of the coefficients of the equations and put them together into one matrix here, which we can call matrix A. We take the elements, so the unknowns, x1, x2, and x3, and we put those into a column vector here. So this matrix times that column vector is now equal to the column vector of b1, b2, and b3. Okay, so that is, of course, in the classic form of A times x equals b, where capital A here is this matrix of a11 to a33. Bold X is now this column vector x1, x2, and x3, and B is b1, b2, and b3 that we see from there. Now, of course, from normal algebra, we know that if we were to solve this, if we wanted to solve this equation ax equals b for x, we would divide everything through by a, which would leave us with x equals b over a. And it turns out that with the matrix notation, we can actually do something similar. So we can write that as a times 1 over a times x is equal to 1 over a times b. And that, of course, gives us that x is equal to a to the minus 1 b. Now, this a to the minus 1 term is what we're really interested in. This is the inverse of the matrix A. And this is one example of a situation where you might want to calculate the inverse of a matrix in order to solve a system of linear equations. However, it is worth noting that this is not always the best way to solve systems of equations. I'm simply using it here as an example of why you might want to calculate the inverse of a matrix, and to give an example to some extent of what the inverse of a matrix really means. So in fact, to expand upon that, I want to start out really by talking Gaussian elimination. Now, this is a better way of solving a system of linear equations, and this provides a very nice lead into talking about Gauss-Jordan elimination in a moment, which we're going to use to actually compute the inverse of a matrix. So let's first of all look at how we can use Gaussian elimination to solve a system of linear equations. Now, our aim is to transform the matrix A into what's called row echelon form, or sometimes called an upper triangular matrix. And that means something that looks like this. So as you see in this example, all of the elements in the lower left are 0. All of the leading elements here in blue are 1, and all of the remaining elements in the upper right, which are coloured yellow here, are all the non-zero elements. They don't have to be non-zero, but it just means that all of the non-zero elements of the matrix are now in the upper right corner, and all the elements in the lower left corner are 0, and all of our leading elements, as you can see here in blue, are 1. So this matrix is now said to be in row echelon form. So how do we actually go about achieving that? So we're going to transform our original matrix using elementary row operations. Now there are 3 of these that we can use. We can add a multiple of one row to another, or we can multiply a row by a non-zero number, and we can swap one row with another one. Now we can use any number of these in any combination that we like in order to get the result that we need. So let's consider a simple example. So let's start with this system of equations here. So we have x plus 3y minus z equals 13, 4x minus y plus z equals 9, and 2x plus 4y plus 3z equals minus 6. Now we're going to work with this system of equations as an example throughout the rest of the slides that I'm going to show. So if you wish to write this down on a pen and paper, then now would be a good time to do so. In fact, actually, I would recommend working through the calculations that I'm going to show here with a pen and paper. Feel free to pause the video at any point to do that, and that should hopefully help you to understand what's going on if anything appears a bit confusing. Okay, so if we write that out in matrix form, we end up with this. So we take the coefficients of our equations here, now shown in blue, 1, 3, minus 1, 4, minus 1, 1, 2, 4, and 3. And then we have the column vector of x, y, and z, the unknowns in white, and the result is equal to 13, 9, and minus 6, shown here in yellow. Now, this might seem a little odd at first, but just bear with me and stick with it. What we're going to do is to augment the far left part, that's this part here in blue, this 3 by 3 matrix in blue, with the right hand side of this equation here. So that's the yellow column vector. And what we end up with then is one single matrix of 3 rows, now with 4 columns. So we see we've taken this 3 by 3 array here of 9 elements from here in blue, and we've simply augmented those with the 3 elements there in yellow to give a new matrix there of 12 elements with 3 rows, 4 columns. Okay. Now we work with that using the elementary row operations that we just talked about. So this is what we're starting with, and then the first operation that I have chosen to do. Now it's worth noting that there are any number of different ways that you could go about doing this. It's not necessary to do it the way I've gone about doing it. Done correctly, all the different possible ways of doing it should result in the same answer, of course. So, but what I chose to do when approaching doing this by hand was to start out by adding minus 2 times row 3 to row 2. Now let's just break down what that really means. What that means is we're going to take row 3 here and we're going to multiply every element in row 3 by minus 2. So 2 times minus 2 is obviously minus 4. 4 times minus 2 is obviously minus 8. 3 times minus 2 is obviously minus 6. Minus 6 times minus 2 is obviously 12. So we're going to take all of those values, in this case 4, 8, minus 8, minus 6, and 12, and we're going to add those to the elements, the corresponding elements in row 2. And if we do that, this is the result that we get. So obviously we get a 4 from here. Minus 2 times 2 is minus 4. So we have there 4 minus 4, which gives 0. And then the other elements accordingly, okay? So we can see how that works. And that is the first element there set to 0. You remember from the example of the row echelon form matrix that we looked at just now, we want all of these 3 elements in the lower left corner to be equal to 0. So we see that we've now achieved that for our first one. So going on from there, the next operation that we do is to multiply row 2 by minus 1 over 9. Now obviously the effect of that is simply this going to divide everything here by 9 essentially. So minus 9 divided by minus 9 is of course 1. So we now set this element to 1. Remember that we're trying to achieve all of our leading elements being equal to 1. And obviously the other elements in that row are modified accordingly. So now starting from there, we now add minus 2 times row 1 to row 3. So minus 2 times row 1, so minus 2 times 1 is minus 2. 2 plus minus 2 is 0. So we see now that we have our second 0 in the first column. And then of course we have minus 2 times 3, which is minus 6. 4 plus minus 6 is minus 2, and so on for the other columns. Okay, but we see we're getting closer to the result that we want. We now have 2 zeros here. Okay. So again, starting from there, the next thing that we do is we add 2 times row 2 to row 3. So we can see we want to get rid of this minus 2. Now row 2 happens to have a 1 in that column, so we can use row 2 to achieve that. 2 times 1 is of course 2, minus 2 plus 2 is of course 0. So we've achieved now the result that we want. We have these two leading elements, both 1, and we have the zeros here in the lower left corner. Now, in fact, because we're talking about solving a system of equations, we can actually stop there. There's no need to carry on to change this one into a 1. We could obviously divide by 6.111 or 6 1/9 in order to change that to a 1, but we don't actually need to do that. So let's see why that is. In order to actually solve the system of equations, we separate this back out again into the form that we had at the beginning. So we take the elements in blue and we put those onto the far left of our equation, multiplied by our unknowns x, y, and z is now equal to these yellow elements that we have over here. And what we can see immediately, if we look at the last of the third row in here, we have 0 times x plus 0 times y plus 6.111 times z is equal to minus 36.6 recurring. So what that tells us is that 6.1 recurring z is equal to minus 36.6 recurring, and that therefore, of course, z must equal to minus 6, allowing for rounding errors. Now, if you're working this out by hand yourself, do feel free to write these numbers out in the precise form using fractional notation if you wish. I have just gone for using decimals here because I thought that was a bit clearer, just to show what was going on. Okay, so now we know that z is equal to minus 6. We can now use back substitution to compute the values of y and x. So in the case of y, we know that 0 times x plus 1 times y plus 0.555 recurring times z is equal to minus 2.333. So we have y plus 0.5 recurring z equals minus 0.23 recurring, and therefore y is equal to 1, simply by solving that equation. And we do the same for x. We have x plus 3y minus z equals 13, therefore x is equal to 13 minus 6 minus 3, and therefore x must equal 4. And if you remember back to the system of equations that we started with, you can see that that is indeed the right answer. Okay, so this video was supposed to be about computing the matrix inverse, so why are we worrying so much about solving systems of equations? Well, that's a very good question, but talking about Gaussian elimination provides a very nice lead into discussing Gauss-Jordan elimination. And what we're going to do is use a similar method to compute the inverse of a matrix. Now, a matrix that can be inverted has the property that a times a minus 1, that's a multiplied by its inverse, is equal to I, where I is the identity matrix. So, for our previous example, we have these coefficients here in blue, multiplied by whatever the inverse is. So remember, this is the matrix A here in blue, multiplied by whatever the inverse of that is, has to be equal to this, the 3 by 3 identity matrix. So what we can do is, just as we did before, we can compute a to the minus 1, the inverse of a, by augmenting the far left-hand side, that's the numbers in blue, the coefficients in blue, with the right-hand side as before. So we take the identity matrix here, the 3 by 3 identity matrix in white, and we augment that into the 3 by 3 matrix that we have here in blue, and that gives us one matrix, now has 3 rows and now 6 columns. Okay, now in order to try and make this clear, I'm going to stick to the same color scheme throughout. So we're going to leave these values, these elements here in white, and these elements here in blue. And now we're going to use the same elementary row operations that we did before to process this matrix in exactly the same way as we did for solving the system of linear equations. So I've written that here. Gauss-Jordan elimination is different in that it simply takes the process further to give what's called the reduced row echelon form of the matrix, where all of the leading elements are 1 and all of the other elements are 0. So as we work through this, we'll see what that means. So our aim is to reduce our matrix from this form that we've just seen here to something like this. So we want to use the elementary row operations that we've already talked about to go from this matrix to this matrix here. So we're going to convert all of these leading elements to 1 and all of these other elements here to 0 in the blue half of the matrix here, and that will give us 9 coefficients over here that will actually represent the inverse of the matrix. So B11 through to B33 is now the elements of a to the minus 1, which is the inverse matrix that we want to calculate. But of course, we don't know what they are at this stage. So we have to use the elementary row operations to go from this to this, and then these elements here in yellow are going to be the inverse of the matrix that we want. Let's have a look at how that works. So first of all, we repeat the steps that we used for the system of equations before to give this. Now, the only difference here, this is exactly the same, except I have now written out the numbers properly using maintaining precision using the fractional notation. So for example, instead of 6.1 recurring here, we have 6 1/9 and so on. Apologies if that is a little bit confusing. Some of the fractions do get quite close together. But if you work through the previous example again, doing it this way, you should end up with the same result. And what we're going to do is simply now continue the process. So we're going to continue the process to ensure that all of these leading elements are 1 and all of the other elements in the blue section of this matrix are equal to 0. So the first thing that we're going to do is multiply row 3 by 1 over 6 1/9. Okay, so 6 1/9 divided by 6 1/9 is of course 1, and we modify all the other elements in row 3 accordingly, and we get these admittedly fairly unwieldy fractions. That's 1 and 13/55, by the way, and that one there is 2 9s. They do get close together. Apologies about that, but hopefully that will be sufficiently clear. So now moving on from there, we now add minus 3 times row 2 to row 1. Okay, so minus 3 multiplied by row 2, and we add that to row 1. Okay, so the objective here, of course, is to get rid of this 3. So minus 3 times this 1 will give minus 3, and we add that to there, which of course then gives 0. And of course, we modify our other elements accordingly. Okay, so going from there, now the next step is to add 8/3 of row 3 to row 1, and that gets rid of this minus 8 over 3 term here. So that now becomes a 0. And you can see now we are very, very nearly there. The only element we have to get rid of now is this 5/9 here, and we can do that very simply by adding minus 5/9 of row 3 to row 2. So notice what we're doing here. So we want to get rid of 5/9 here. So we look in that column to find a row where there's a 1. If we have a row there where there's a 1, that becomes very easy because we simply multiply that 1 by minus 5/9 and then add it to this row, and that will have the effect of removing that. So now you can see our elements here in blue now form an identity matrix, and the elements here in yellow actually do now contain the result that we want. This is the inverse of the original matrix A. And we can write that down in decimal notation. We see we get this. Now, I have used other software to verify this result, and I do believe that it is correct. The interesting question comes that how would you verify that this is the right result if you didn't have other tools that you could use to actually check? Because obviously, if you have other tools that you can use to check, then, well, what was the point of calculating it yourself in the first place? It doesn't make any sense, right? Luckily, there are 2 different ways we can actually verify whether or not we have got the right result. So, the first way we can do this is to consider the identity that we started with. We know that A multiplied by its inverse, A times A to the minus 1, is equal to I, the identity matrix. Okay, so we can test if that is indeed the result we get. So we start with our original elements of A, shown here in blue on the left-hand side, and we multiply those by the elements of the inverse that we've just calculated, shown here in yellow, and we're going to put the results over here, and we'll see if we end up with the identity matrix. Now, I've talked about matrix multiplication in my previous video. I'll put a link to that in the description below, so if you don't understand what's going on, I suggest you go back and have a look at that, but I will talk about it briefly. So basically, to do this, the first element of the result we get from multiplying 1 from here times 0.1272 from here, plus 3 times 0.1818 from here, plus minus 1 multiplied by minus 0.3272 from here, and that gives 0.9977, which is the first element of our result, and that's pretty close to 1, allowing for rounding errors. Then we do 1 times 0.2363, plus 3 times minus 0.0909 plus minus 1 times minus 0.0364, and that gives 0, pretty much within rounding errors. Okay, And then we're going to do 1 multiplied by minus 0.0363 plus 3 multiplied by 0.0909 plus minus 1 times 0.2363, and that gives 0.0001, or 1 times 10 to the minus 4. And we put that in. And if we continue with that process, we will end up with the result that we see here. So what we see is that the leading elements here are all very close to 1 within rounding errors, and all of our other elements are indeed very close to 0. That one, that one, that one, that one, that one, and that one. That is, within rounding errors, close enough to the identity matrix that convinces me that we do indeed have the right result. Now, if you were to use the exact fractional notations of versions of these numbers to maintain precision, I think you would get exactly the identity matrix there. But obviously, because I've rounded them, we don't quite get there, but it is close enough. So that is one way to tell that we do indeed have the right answer. Now, we also know that x, our original unknown values, is equal to a to the minus 1 times b. So we can write that out. So we can write out the coefficients here of the inverse of a that we've calculated, multiplied by b, which if you remember was 13, 9 and minus 6. And we can use this to calculate the values of x, y and z. So if we do that, we get x, y and z is equal to this 3.9981, y equals 0.9999, and z equals minus 5.9990. So again, allowing for rounding errors, that is pretty close to x equals 4, y equals 1, and z equals minus 6. And those are the values that we began with. So we can see that that is indeed the right way of doing it. Okay, and as I say, that is close enough there to the original values of x equals 4, y equals 1, and z equals minus 6. Okay, so that's really everything that I wanted to talk about today. As I said in the introduction, I really just wanted to focus on covering the basic theory behind Gauss-Jordan elimination and how we can use that technique to calculate the inverse of a matrix. So in this video today, we've seen how we can use Gaussian elimination to solve systems of linear equations, and then we've seen how that provides a nice lead in to talking about Gauss-Jordan elimination and how we can use that process to actually calculate the inverse of a matrix. It's worth noting, of course, that not all matrices are invertible. A matrix that is invertible has to be square, and it has to have a determinant that is not equal to 0, which means a matrix with a determinant equal to 0 is known as a singular matrix, and those cannot be inverted. However, they are numerically quite rare compared to invertible matrices, so it's quite often not something that we need to worry about, but it is worth bearing in mind that not every single square matrix can be inverted. Okay. So that just leaves me to say, I really hope you've enjoyed this video. I really hope you found it useful. It's been a great deal of pleasure making it. If you have any feedback or comments or anything, really please do let me know in the comments below. It is always good to hear from you. I like to know what people think of my videos, and yeah, it's just good to know that, you know, great to know what you think. And yes, so in the video next week, I plan to go on to look at how we can write code to implement this algorithm. So we've seen how it's a kind of a process, and it's one of those algorithms that's relatively easy to do by hand, but becomes quite difficult to think about how to actually go about writing code to implement it. And I think this is why I said in the introduction that I think this is a really very nice example of a computational algorithm, or dealing with a mathematical problem by writing a computational algorithm to implement it. I think this is, as examples go, a pretty good one. So that's coming up next week. So if you haven't subscribed to my channel, please consider doing so, so that you don't have to miss next week's video, or indeed any other videos. I do try to post a video roughly once a week, so if you subscribe, you don't need to worry about missing anything. If you've liked this video, please remember to smash that like button. And once again, thank you very much for watching. It's been a pleasure, and I really look forward to seeing you in the next video. Bye!